In 2020, Elon Musk stood on stage and said 3 words that were supposed to redefine the automotive industry: forever structural battery. The battery becomes the floor. The floor becomes the structure. Dead weight disappears. The automotive press called it the engineering breakthrough of the decade. Nobody questioned it. Nobody verified it. 3 years later, the Cybertruck arrived. It weighs 6,843 pounds, the heaviest production pickup truck in American history. Its battery sits in a sealed enclosure. Its stainless steel body is its own separate structure. Its frame is a third independent structure beneath both of them. 3 structures, 3 weight penalties, none of them doing the other's job. Meanwhile, in Guangzhou, Xpeng forged a single piece of aluminum front-to-rear body to load path that achieves 46,000 Newton-meters per degree of torsional rigidity. No separate enclosure, no separate frame, one structure, one weight budget. Musk described the future correctly in 2020. He just didn't build it. Someone else did. To understand why the Cybertruck's architecture matters, you need to go back to 2020, not to the Cybertruck reveal, but to the Battery Day presentation that followed it. That night, Musk didn't just announce a new product. He announced a new physics. The structural battery pack, he explained, would function simultaneously as energy storage and as the load-bearing floor of the vehicle. By merging 2 systems into one, Tesla would eliminate the mass of the enclosure, reduce part count by 370 components, and cut battery pack cost by 10%. It was not marketing language. It was an engineering thesis delivered with specific numbers to an audience of engineers and investors who had no reason to doubt it. Tesla did implement structural battery technology in the Model Y. The rear underbody of the Model Y uses a version of this architecture, and it works. It reduced the Model Y's mass and simplified its assembly. The press reported it accurately. The public understood it as Tesla's standard approach going forward. The mistake was assuming the Cybertruck inherited the same logic. It did not. When Cybertruck engineers faced the unique demands of a stainless steel exoskeleton, a material that cannot be stamped, welded, or integrated with battery cells, in the way aluminum can, the structural battery concept was quietly abandoned. The enclosure came back. The frame came back. The dead weight came back. But the terminology stayed. Nobody corrected the record. And 6 years after Battery Day, the American public still believes the Cybertruck is built the way Musk described. It is not. Every vehicle has a weight budget. Engineers call it the mass breakdown, a precise accounting of every kilogram in the vehicle organized by system. Powertrain, chassis, body, battery. Each system competes against the others for grams because every gram added to the structure is a gram subtracted from range payload or towing endurance. The Cybertruck's mass breakdown reveals a structural decision that contradicts the promise of Battery Day. The stainless steel exoskeleton, 301 grade cold-rolled stainless chosen for its yield strength of 517 megapascals, adds approximately 1,000 pounds of body mass before a single battery cell is installed. This is not a consequence of the vehicle's size. It is a consequence of the material. Aluminum, the standard body material for lightweight vehicles, can be cast into integrated structural forms that share load paths with adjacent components. Stainless steel cannot. It must be stamped into panels welded into a monocoque and structurally isolated from the battery system beneath it. The result, the Cybertruck carries 3 independent structural systems simultaneously. The stainless exoskeleton provides body rigidity. A separate reinforced battery enclosure estimated at 180 to 220 kilograms of housing mass alone protects the 123 kilowatt-hour pack. And beneath both sits a steel frame that provides the towing and payload foundation. None of these 3 systems shares a load path with the others. Each one adds mass. Each one adds cost. And each one is by definition dead weight relative to the other 2. Compare this to the architecture Xpeng deployed in the X9. A single gigacast aluminum structure, front and rear sections forged as one continuous piece by a 12,000-ton die casting machine, carries the structural load of the entire vehicle. There is no separation between the body's load path and the battery's mounting structure, because they occupy the same object. The result is 46,000 Newton meters per degree of torsional rigidity, achieved not by adding structure, but by eliminating the gaps between structures. The Cybertruck's torsional rigidity, measured independently, sits between 14,000 and 17,000 Newton meters per degree. That is not a failure of the stainless steel. That is the predictable consequence of building three structures where one was promised. Weight is not an abstract engineering metric. In a pickup truck, weight is a sentence of fixed penalty that the driver serves on every mile, in every condition, whether the truck is empty or loaded. And the Cybertruck sentence is the heaviest ever handed down to a production pickup in American history. At 6,843 pounds of curb weight, the Cybertruck AWD enters every trip carrying approximately 900 pounds, more than a fully loaded steel Ford F-15. Oh, with no passengers. At 65 miles per hour on a flat Texas highway, aerodynamic drag and rolling resistance consume energy in direct proportion to mass. Independent testing by engineering analysts at Monroe and Associates and data published by the EPA confirm that every additional 100 pounds of vehicle mass reduces EV range by approximately 1 to 1.4% at highway speeds. Applied to the Cybertruck's structural weight overhead, conservatively estimated at 600 pounds, above what an equivalent integrated architecture vehicle would weigh, that penalty alone accounts for 8 to 12% of range lost before the driver touches the accelerator. The consequence is measurable and specific. The Cybertruck AWD delivers 320 miles of EPA range. An equivalent vehicle, same pack capacity, same motors, same aerodynamic profile, built on an integrated gigacast architecture with no separate enclosure and no redundant frame structure, would carry that same energy budget in a body weighing an estimated 6,200 to 6,250 pounds. At highway speed, that weight reduction translates to approximately 30 to 38 additional miles of range. Not from a bigger battery, not from a more efficient motor, from the structure that was supposed to disappear in 2020. Now place that calculation on a real American driving scenario. A Cybertruck owner in San Antonio, Texas, hooks up a 10,000-pound trailer and heads west on I-10 toward El Paso, 558 miles of highway, with charging infrastructure that thins dramatically after junction. Towing at 65 miles per hour, the Cybertruck's real-world range collapses to approximately 120 to 150 miles per charge. That is not a battery problem. The 123 kilowatt-hour pack is large by any standard. That is a weight problem, and the weight problem is a structural problem that was identified, named, and promised to be solved in 2020. The X9's integrated gigacast body weighs approximately 38% less per unit of torsional stiffness than the Cybertruck's three-layer structure. When that ratio reaches truck-scale production, the San Antonio driver does not stop in Junction. He does not stop in Ozona. He reaches El Paso with margin to spare, not because China built a better battery, but because they built less structure. The machine that built the Xpeng X9's body does not look like an automotive tool. It looks like infrastructure. At 12,000 metric tons of clamping force, Xpeng's die-casting press is among the largest mass production machines operating anywhere on Earth. The aluminum enters as liquid. It exits as a vehicle, not a vehicle component. A vehicle. The front and rear body sections of the X9 are each cast as a single continuous piece. No welds between the A-pillar and the firewall. No adhesive bond between the floor and the sill structure. No mechanical fasteners joining the rear quarter to the cargo floor. Where the Cybertruck requires hundreds of individual stampings joined by thousands of welds and fasteners to create a body structure, the X9 requires two castings. The complexity that creates mass in the Cybertruck's architecture, the tolerance stack between panels, the reinforcement required at each joint, the additional material needed wherever two separate components meet, does not exist in the X9's body, because the joints themselves do not exist. The physics of this distinction is not subtle. Every joint in a vehicle body is a point of potential compliance, a location where under torsional load, the structure can flex slightly before load is transferred to the adjacent component. In a body assembled from stamped panels, these compliance points accumulate. The stiffness of the final assembly is always lower than the stiffness of its individual components, because the joints between them are the weakest links in the torsional chain. This is why the Cybertruck's three-structure architecture, each element stiff in isolation, produces a combined torsional rigidity of 14,000 to 17,000 Newton meters per degree. The structures are stiff. The gaps between them are not. The X9 single-cast architecture eliminates the gaps. There is no joint between the front structure and the rear structure. There is only structure. The result, 46,000 Newton meters per degree, is not an improvement over conventional architecture. It is a different category of answer to the same question. And when that category of answer is applied at truck scale, with pack integration replacing the enclosure mass and a single casting replacing the three-structure penalty, the weight sentence that Cybertruck owners serve on I-10 becomes commutable. The 12,000-ton press in Guangzhou is not a manufacturing curiosity. It is the physical proof that the promise Musk made in 2020 was technically achievable. It simply required building it the way the physics demanded, not the way the stainless steel panels allowed. The gap between the Cybertruck's architecture and the X9's gigacast body is not a product gap. It is a manufacturing gap, and manufacturing gaps in the automotive industry do not close in a product cycle. They close in a generation if they close at all. Consider what it would take for Tesla to rebuild the Cybertruck's architecture around an integrated gigacast body. The stainless steel exoskeleton is not a design preference. It is the foundational identity of the product, the feature that Musk committed to publicly, that the reservation holders paid deposits to receive, and that the Fremont factory was retooled to produce. Abandoning it does not mean a redesign. It means a new vehicle, a new factory configuration, a new supply chain for aluminum casting at scale, and a new die casting infrastructure that does not yet exist at Fremont in the form required. The 12,000-ton presses that Xpeng and other Chinese manufacturers now operate were not purchased off the shelf. They were co-developed with suppliers over years of iterative production. Tesla would be starting that process from the beginning. The capital cost of that transition is not speculative. Xpeng SEPA 2.0, manufacturing build-out, including gigacast press infrastructure, aluminum alloy development, and the thermal management integration required to make cast bodies compatible with battery systems, required an investment cycle measured in billions and a development timeline of 3 to 4 years before the first production unit. For Tesla, a company currently managing margin pressure across its entire lineup, initiating a parallel architecture program for a vehicle that represents a fraction of its total volume is not a straightforward financial decision. It is a bet that the market will wait. The market may not wait, because the manufacturing gap is not limited to Tesla. It applies to every American automaker that is committed to large format battery trucks. General Motors' Ultium platform, which underpins the GMC Hummer EV, and the Silverado EV uses a modular pouch cell architecture mounted in a dedicated floor enclosure within a traditional ladder frame. Ford's Skunk Works EV programs for next-generation trucks have not publicly committed to structural battery integration at the gigacast level. Stellantis, which produces the Ram 1500 REV, is carrying 229 kilowatt-hours of battery capacity in a dedicated enclosure that adds mass without adding structural contribution. Every one of these programs represents billions of dollars of committed capital factory retooling and supply chain contracts that were structured around a conventional battery enclosure architecture. Pivoting to integrated gigacast production is not a software update. It is a physical factory problem, and physical factory problems have physical timelines. Meanwhile, Chinese manufacturers are not pivoting. They are scaling. CATL's Kirin 3.0 platform, which integrates thermal management and structural load-bearing function directly into the cell layer, is in active production deployment. BYD's cell-to-chassis technology is expanding across vehicle classes. The gigacast press capacity being installed across Chinese manufacturing facilities in 2025 and 2026 is not experimental. It is industrial. The question for American workers in Fremont and Warren and Sterling Heights is not whether this technology will arrive at truck scale. It is whether their factories will be building it when it does, or whether they will be building the structural equivalent of a promise that was made 6 years ago and never fully kept. That is not a question about China. That is a question about American manufacturing strategy, and the answer is not yet written. Elon Musk was not wrong about the physics. Structural integration works. Gigacasting works. Eliminating the separation between body enclosure and frame works. The engineering thesis he presented at Battery Day 2020 was correct in every dimension that mattered. What he built was something else. The Cybertruck is not a failure of vision. It is a failure of follow-through a product that inherited the language of a breakthrough without inheriting its architecture. And in the 6 years between the promise and this moment, the architecture found a different address. It found 12,000-ton presses in Guangzhou. It found gigacast bodies in production. It found 46,000 Newton meters of torsional rigidity in a vehicle that costs a fraction of what the Cybertruck commands. The question American manufacturers now face is not whether integrated gigacast architecture will define the next generation of electric trucks. It will. The question is who will be operating the presses when that generation arrives, and whether the factories in Fremont and Warren and Sterling Heights will have made the capital commitment, the supply chain investment, and the engineering pivot in time to be part of that answer. History does not wait for the heaviest truck in the room to catch up. The promise was made in 2020. The physics were always there. The only thing that was missing was the willingness to build it the way the physics demanded, not the way the panels allowed. Someone built it. Just not in California.